So let's kick off our new unit on magnets and learn about what exactly magnets are and how they work. First of all, magnetic forces. There's this attraction and repulsion, very similar to the electrical forces we've been learning about earlier. And first of all, the like poles, so similar poles will repel and opposite poles will attract. So north poles will repel north poles and south poles will repel south poles. But if you have something that has a different pole, so north and south will actually attract each other. And of course, the force between the poles will depend on the separation and distance between them, just like electrical forces. So we're kind of at home already with magnetic forces because they're very similar to electrical forces. And you're also going to see that electricity overlaps quite frequently with magnets. So magnets all have two poles. They have a north-seeking pole, which means that it points towards the north end of the Earth, and then a south-seeking pole, which would be attracted towards the south end of the Earth. And this north and south, just two different sides, are what give magnets basically it lets them work the way they do. So if you look at this picture, between the north and south poles, there is this force of attraction between the south and north. But if you put two norths near each other, they are going to repel. So these poles are pretty important. Now, the big difference between electrical force and magnetic force is that basically electric charges, we can isolate them. You can have a single negative particle we call an electron and a single positive particle we call a proton. But for magnetic poles, it's a little bit different. No matter how much you cut a magnet in half and break it down and break it down and break it down and break it down, you're still always going to end up with a north and south pole. So we can't isolate and just have a north pole or a south pole object. It has to have both. So keep on cutting. It doesn't matter. You're not going to get just a single north pole. On the other side of it will always be the south pole. Now, just like electric fields, magnets give off fields of energy too. And it always flows from the North Pole to the South Pole. So if you look at this picture over here, all of the magnetic fields are going from north to south. And they bow out and come back in. You've probably seen this before as a younger kid, maybe in elementary school. You had a bar magnet and you used iron filings, and you could actually see the magnetic fields being traced by the iron filings. It was just showing you the magnetic fields. Now, where the lines are closer together, just like in electric fields, the closer the lines are together, the stronger the field is. And that makes sense. Some magnets are stronger than others, and we're going to see that more and more as we do some labs. Now, electron spin in atoms, as you've learned in chemistry, there's always a spin up and spin down. But in atoms, when you have solo or lone pair electrons, something like an iron, it has 4 lone pair electrons in different little orbitals. Those can all have the same spin. If you have electrons that end up having the same spin, you start to get a strong magnet. That's because the ones that have the same spin start to create these strong interactions which form this field, and you end up getting a north and south pole. Now, for electrons in atoms, I should say, that have opposite spins and they start going all in different directions, they actually cancel out. So in a chunk of iron, say, all the electrons that are lone pairs start spinning in the same direction. For all the different atoms, all of a sudden you have a lot of organization and you start to get a positive and negative end, or a north and a south end. So I want to talk about magnetic domains. And basically, if you have a chunk of an element in your hand and all those atoms, lone pairs, that can start spinning in the same direction, your atoms in the element start lining up in the same direction as well, where the North Pole all points one way and the South Pole all points the other way. When you get that organization, you get a magnetic domain, so you have a magnet. But when your magnetic domains aren't arranged and they're all in different places, so your North and South Poles are all over the place, you are not going to get a magnet because those domains are going to cancel out. So think of a magnet as a pretty organized element or substance where all the north poles are pointing the same way and all the south poles are pointing the same way. That organization of the domains is what allows a magnet to be a magnet. Now, something interesting is we can actually create a magnetic field from electric current. And if you really start looking into this in the internet, it's fascinating because we don't exactly know why. We just know if you're running an electric current and you're running and moving charges through a wire, you actually produce a magnetic field, which is pretty fascinating. So what we've just been learning about with electricity, it can also be the cause of a magnetic field. Now, we can take advantage of that by coiling or wrapping around an electric wire around objects, and the more we coil it, like right here, the more electromagnetic field we can create. And from that, we can create these super magnets that can pick up things as big as cars and move them around with the crane-like apparatus. So we can actually create electromagnets by simply running a current coiled around something like a nail and connecting and completing the circuit. And we understand how electricity flows through a wire from the negative end to the positive end. So we could easily make this and create a little magnetic field. And that's what we're going to do eventually in class. So how do electromagnets work? Well, if you have an electric current running through a wire, yeah, you are going to get a little magnetic field. But if you start coiling the wire more and more, you get an even stronger electric field. Forgive me, not only an electric field, but a magnetic field. And then if you coil it around something even more so, like a nail or a piece of metal or iron, you get an even stronger magnetic field. And so this is eventually what we're going to do in class. We're going to take a battery with some wire, coil it around and around and around and around a nail. And what we'll see is that simply by putting that current of electricity through that nail and those coiled wires, you're going to create a magnet, which means there's going to create a north and a south pole, which will attract other metal objects. All right, so we just touched on the beginning ideas of a magnet, but do realize that all magnets have a north and south pole, that an electrical current can create a magnet, and the idea of magnetic domains. When objects, or I should say atoms in an element, all start aligning in similar ways with the north and south pole, you get a stronger and stronger magnet. All right, welcome to magnetism. We'll keep on going.